Okay, welcome back to class, everybody. It's a pretty good time to get started. So let's begin by briefly reminding ourselves what we discussed last time. So we spent the majority of class going over homework 1. So I showed you how I programmed that particular homework assignment. And it's something that I forgot to tell you at the beginning of class when we started class several weeks ago. But one thing I can promise you is that every homework assignment that I give you, I program before I actually give it to you, which is not a promise that many of your professors can make when they give you homework assignments, okay? So I know exactly what you guys are going through and like the problems that you guys have to solve to turn in that particular homework. So in going over that homework assignment, we learned a little bit about organizing code, and we learned some interesting things about sci-fi. In particular, you learned about broadcasting and how useful that is and how it can speed up your programs at the cost of a little bit of memory. And then we learned about two really useful tools, which is the Python debugger and profiler. So the debugger I use all the time, like all the time. When I'm running my code in the IPython interpreter and it throws up some exception that I don't know why it is, I almost immediately type %debug to jump down to where that exception was and walk up and down the stack trace to figure out like exactly what caused it. So the debugger, super useful. The profiler I use less often because it's really only useful when you really need to speed things up, right? So most of the time, if you're careful and you think about how long things take, your program is going to like run at a time that's acceptable for you. But sometimes when you're writing scientific code, like it's really important for it to run fast. And at that point, you might start looking at the profiler and start experimenting with different ways of doing things to make sure that your program runs fast. And we might run into some of that in our future homework assignments. And then we spent just a little bit of time talking about homework 2, which was a homework to allow you to play a little bit with geographic plotting and pandas. And so hopefully many of you have gone a good way into doing homework 2. And maybe a good way to start class today is if you have any questions on homework 2, please ask them now. Because if you have the question, there's a good likelihood that 50% of the rest of class has the same question. Yeah?
Is there anything special you would have to do to implement the code that you gave to make the AVI file?
So yes, so that is not code. That's a command line. That's a command that you run. And the first word of that command is a program called mencoder or mencoder. And what that does is it's a program to just that does a lot of things, but it converts video files. And one of the things that it does is it takes separate images and can combine those into the frame to make the video. And so to execute that program, it either has to be installed on your laptop or you can run it on the machine that I gave you all logins for where that program is installed. Or a third option for you is to find one of many other programs that take a list of images to create a movie. So I don't care which way you do it. The only reason that that's listed in the homework assignment is to make sure that I give you at least one way that you can complete, which is to use the computer that I provided you logins for and that particular command. So other questions? Yes?
In the example video, I think you have the year number on the figures. Do we have that on?
Absolutely. Yes, I want the year number on there because that's an important part of understanding how to work with Matplotlib. Other questions? Okay, if not, the plan for today is to begin by doing some interactive Python programming and discuss about generating random points, both in a space and generating random directions. And this is just an important building block of some of the future assignments that we're going to make, and something that comes up over and over again in scientific computation. And then we're going to spend the majority of class talking about stochastic gradient descent. So your next homework assignment is going to be our first one where you have to implement an actual optimization algorithm by building up sort of a complex code base. And that optimization algorithm is going to be this one, stochastic gradient descent. And I picked this one because it's really at the core of essentially all large-scale machine learning problems these days. So this is like the algorithm that gets used when you have a billion item database and you want to do some kind of machine learning from those examples, okay? And we are going to use it on some machine learning problems on the next assignment, but for the first assignment, we're going to use it on just some mathematical problems that allow us to understand how the algorithm works and allow us to visualize its progression. So we're going to start by introducing the next homework assignment. We're going to go through some proofs and discussion of the algorithm. So typically in this class, I would never do a proof, okay? But this proof is actually important. And the reason it's important is because for stochastic gradient descent to work, there are some assumptions that have to hold true. And it's very easy to write your code in such a way that those assumptions are not true, and then the algorithm doesn't work. And I might have you run some of those examples to see that the algorithm just produces garbage answers if those assumptions are not met. And the only reason, or the only way to understand why those assumptions are important is to actually go through the proof that the algorithm works. Okay, so we're going to look at that proof in some discussion. And then we're going to look at parabolas and how to apply stochastic gradient descent to parabolas, which is going to be our first homework assignment on this algorithm. And then, depending on the extra time that we have towards the end of class, I'm going to introduce you to two useful Python modules that you should know about. They're called Shelve and Pickle. The reason I'm introducing you to them is because we're going to use them in some future homework assignment. And they're the basic way that you can store a bunch of data in Python and then like load it back into your program later, right? So that's a really useful operation, especially if you're doing some kind of really complex computation and you stop your program in the middle and you want to like pick it up from where it left off. At that point, you might want to store that to disk and sort of like load that back in memory and continue from there. So Shelve and Pickle are quite useful. And then, should we have even more time, we're going to do some in-class programming, and we're probably going to just test whether our generating of random directions actually is generating random directions, or if we had a bug in our code. So in general, whenever you code something, it's important to pass in some examples where you can test whether it's actually producing the kind of result that you want it to produce. So an example where you know the answer so that you can check whether your code's actually producing that answer. And so we have a couple of options here. So one is testing whether this generation worked, and another is to actually implement stochastic gradient descent on a 1D function. But we'll probably just do the testing directions. Okay, so let's just begin by talking about generating random points and directions. Okay, so I'm just going to open up the interactive IPython interpreter here. And my first question is, imagine the square in 2D that's just has a side of length 1, let's say between 0 and 1, and then 0 and 1. So let me just draw it here quickly. So let's say this is the x-axis and this is the y-axis. And this is 0, and this is 1. And that's 1, and this is 1, 1. So how would I generate a uniformly random point in that square in Python? So you can tell me, if you don't know how to do it in Python yet, you can tell me how you would do it just generally, and then we'll figure out how to do it in Python. So anybody?
We can, for both the dimensions, we can do it randomly.
So what do you mean by randomly?
Right. We create two random numbers between 0 and 1.
That's right. So two uniform numbers, right? So one between 0 and 1, that's going to pick a uniformly random point across the x dimension. and one uniformly random between 0 and 1 that's going to pick a point on the y direction. So we're going to go uniform here and uniform there, and that's going to give us a uniformly random point over there. So let's see how to do that in Python. So SciPy has several useful modules for generating random things. So one is scipy.random, and it gets imported by default, so that's why it says no module called scipy.random. But if you look at scipy.random, there's all kinds of useful things here, like random sample, random, uniformly distributed bytes, permutations, shuffling, picking a sample from an array that you pass in, and so forth. Okay, so you guys can read over these, but most of the time you don't even need this module because there's a few other built-in functions. So the two most commonly used ones are scipy.rand and scipy.randn. So let's see some documentation about both of these. So scipy.rand, so if I pass d0 up to dn, it generates random values in a given shape. So create an array of the given shape and populate it with random samples from a uniform distribution over 0, 1. Okay, so can you tell me how to generate, let's say, 1,000 random points on that 2D square using this function? So anybody? So I want 1,000 random points on the 2D square that we just saw by using this function. Okay, so you're saying rand, and what do you want to pass in? You want to pass in 0 and 1. Okay. So not quite. So not quite. Does somebody else want to try?
1,000 and 1,000.
So you want to do 1,000 and 1,000. And what is that going to do? So it generated an array. It was really fast. But what did it actually do? So what's the shape of this array? Okay, but I want 1,000 uniformly random points on that 2D square. So not quite. So can somebody fix this? Like, we're getting closer. 1,001, it's like getting closer. Okay, so what does this do? Yeah, it generated 1,000 uniformly random numbers, but it's an array whose shape is 1,001. So did this generate 1,000 uniformly random points on the square? Yeah, 1,002, right? So now what am I doing if I do 1,002? So how did I generate 1,000 uniformly random points on the square? So each row is 1 point, right? And the first column is the x-coordinates of the points, and the second column is the y-coordinates of the points. Does that make sense? Okay, so let's just plot these to make sure that it sort of looks right. Let's just see if it looks right. So answer is scipy.rand, and then I'm just going to do pylab.scatter, which is a scatter plot, and it takes some x-coordinates and some y-coordinates, if I remember correctly. And of course, I didn't do this quite correctly because I want all the rows and the 0th column and all the rows in the first column. And so, looking pretty reasonable, right? But there's a lot of things that could look reasonable here. Does anybody know how you would go about checking if this is actually doing what you want?
We did number of times and see if the mean is the same as the mean for the distribution.
Good idea. So you want to repeat it many times, and you want to check if its mean is equal to the mean of the whole distribution.
Yeah, but that sort of like doesn't verify it, but if it doesn't...
Okay, so the mean of the whole distribution here would be something like 0.5, right? And one thing that satisfies what you're doing is just like generating things on this plus sign that's in the middle, right? So its mean's going to be 0.5, but it doesn't actually do uniform.
If it doesn't match, then we know for sure it's not working.
Okay, so...
It doesn't verify, like, if you get the correct one, it doesn't say that.
So any other ideas on how to check if this is actually generating uniformly random points? Okay, so how many of you guys know about the chi-square test? Just show of hands, anybody? Okay, so I'll tell you about the chi-square test later in class. Fantastic. We're going to program the chi-square test to check for uniformity. So what chi-square test does is it takes some samples from a distribution, and it checks whether it's plausible that these samples came from a distribution that you think they should come from, okay? And the way that you would do chi-square here is you would take this whole space and you would split it up into little tiny grid points, right? And the amount of the 1,000 points that fall into that little tiny piece of grid should be proportional to its area, right? So then I could run the chi-square test counting how many points actually fell into that grid cell versus its area. And the chi-square test will either accept or reject the null hypothesis that these points are actually uniformly random. So partly the reason I'm bringing this up is because last time I taught this course, we did a sequence of assignments that were all on generating uniformly random points from a set. This square is relatively easy because we could do it with two independent uniform variables. But you might imagine a much more complicated region, like some sort of like region that's defined by a bunch of constraints, convex constraints that specify how x and y have to be related within each other, and you want to generate a point within this convex region. So there are then complicated algorithms to generate random points from such regions, and after you implement one of those, of course, you have to test whether it's actually working, and then you would do a chi-square test. So the previous set of students that took this class went through those assignments, but I'm substituting those out for the stochastic gradient descent assignments that we're going to do this semester. Okay, so now that you know how to generate uniformly random points in a grid or in a little square, my next question is, how do I generate uniformly random direction? So to draw that, I mean something like this. So here is y, and here is x. And I'm not very good at drawing it, but imagine that this is a perfectly drawn circle whose center is at 0, 0, okay? So a uniformly random direction means that I generate any of these directions that point in any of the directions emanating from 0, 0 equally likely. So does anybody have any ideas on how to generate a uniformly random direction?
We could generate a uniform number on 0 to 2 pi.
Okay.
And we know the length of the vector, we just need the direction. So the direction with the theta angle that it makes will be a uniform random number.
That's pretty reasonable, and it works quite well. So what if I wanted to generate a uniformly random direction, but now in a higher dimensional space? So I could draw two dimensions really nicely, but imagine that I want to generate a uniformly random direction in 3-dimensional space, or 4-dimensional space, or in general, k-dimensional space. How would you do that?
The dimensions will be independent, so you could generate in each of those dimensions from 0 to 2 pi and get the rest.
And then you'd have to do a lot of complex trigonometry to figure out how to spin things to actually get to the direction that actually is there. Okay, I'm going to show you an even easier way, okay? So I'm going to show you by first plotting something else. So we saw the rand function. It generated uniformly random things between 0 and 1. So let's take a look at rand n. So rand n, return a sample or samples from a standard normal distribution, so just a Gaussian distribution. And there's a bunch of more documentation, but it basically works the same way. You pass in the shape, and it's going to generate a bunch of Gaussians. Okay, so let's go back to our code. And the same way that I generated 1,000 points in 2 dimensions using rand, I'm going to generate 1,000 points in 2 dimensions using rand n. Okay, so before I scatter plot this, does anybody know what it should look like? So what does a 2-dimensional Gaussian look like? It's symmetric, and it looks like a bell shape that's all rotated around 0, 0, right? So when I scatter plot these points, what should I see?
In the center, circular concentration.
Yeah, they should basically look like a circle, but a bunch of more of the points should be around 0, 0 than they should be farther out from 0, 0, right? Okay, and roughly that's kind of what we expect. Right, so 0, 0 is roughly at the center of this concentration of points, and it gets sort of sparser and sparser as you get farther away from 0, 0. Okay, so given this picture, can somebody now give me an idea of how to generate a uniformly random direction? And let me maybe give you a hint before actually before you give me the answer. So for a uniformly random direction, I have to take one of these slices, okay? So let's say that this slice has some angle on it, like let's say 30 degrees or whatever in radians if you want. And here's an equal one that's also 30 degrees. And I want the probability of generating both of those to be equal, right? So the probability that the direction lands in this right one should be about the same as the probability that it lands on the left piece of pie, if you think about it as 2 pieces of pie in the circle, right? So given that hint and this picture, do you have any idea now of how to generate a uniformly random direction? And then what? So how about this? Like each of these things, like the only thing that's different about them is sort of how far away they are from 0, right? And this Gaussian is perfectly symmetric around 0, 0. So I could take these points and normalize them so that they all have a distance 1. So just think of them as vectors and normalize them so that they become unit vectors, right? And when they're unit vectors, because the Gaussian is totally symmetric, each piece of the pie is going to have the same amount of probability that falls in it. And this trick works with any distribution that's symmetric in this way. As long as when you spin it around 0, 0, like each direction looks the same, right? So let's try that, and let's plot it to see if it actually looks as though we're generating uniformly random points on the circle or not, okay? So I have answer here, and I want to do something like normalize it. So let's just do import SciPy linear algebra, and then the norms are going to be SciPy linear algebra.norm of this answer, and I want the 2 norm, and I want it along the first axis. Okay. And I'm not using it right, so let's take a look quickly at the documentation here. And this is a slightly different function than, so SciPy goes through a number of iterations, so slightly different than the one I have on my machine. And you'll notice that partly because this open source software just gets updated quite regularly. So let's just do it ourselves. Let's just compute the norms ourselves. So SciPy square root answer times answer. Sum across the first dimension. So now I have 1,000 vector norms for my 1,000 vectors, right? So now I just want to normalize those vectors. So here it is. I take those vectors and I want to set them equal to themselves over norms. And here, so far we've learned that I could expand dims, right, to do the broadcasting correctly, because answer is 1,000 by 2, and this is 1,000, so the broadcasting doesn't work, right? I want this to be 1,000 by 2, and the second one to be 1,000 by 1. So I have to expand the last dimension of norms. But another way to do that is to just reshape. So I could say reshape to 1,001, and that's going to take that row vector and turn it into a column vector, okay? So now I have my normalized vectors, and let's scatter plot them to see what it looks like. And it looks like really nice, right? It's looking pretty uniform on that circle. Or at least we're not seeing any sort of bunching in one area over another, okay? So let's just do the same thing. So I want to do the same thing, but I want to do it with points that we generated from the square instead of from the normal. Okay, so I want to change answer to be those points that are uniformly random on a square, and this square was between 0 and 1, but I want to move it so that it's centered at 0. Okay, so I'm going to subtract 0.5 from that. So let's take a look at what answer looks like, and it looks reasonably okay here. And let's go through our same normalization trick. So I have to figure out the norms, and then I have to normalize answer, and then scatter plot it. So it also looks not, I mean, visually it's hard to tell, right? Visually it's hard to tell. If I had less than 1,000 points, you will probably be able to notice some bunching around these corners, okay? And that's because the square has a lot more probability around the corners. Like if you look at a pie facing towards the corner, there's a lot more probability weight there than a pie facing either in the y direction or in the x direction. But the point here is that visually it's difficult to say. And so that's why it's important to actually run some tests on your problems to see if they're actually producing the results that you expect them to produce, okay? And so if we have some time towards the end of class today, we're going to run some chi-square tests that hopefully tell us that the normal way of generating uniformly random direction actually generates one, and this square-based way actually does not, okay? The important thing, if we don't get there, the important thing to remember is the following. If you want to generate uniformly random direction in n-dimensional space, you generate n uniformly random Gaussians, and you normalize that vector so that it has a unit direction, okay? So that's much, much easier than the complex trigonometry that you outlined a little bit earlier. So as you can see, it's maybe 2 lines of SciPy code as opposed to many, many lines. Okay, so any questions about generating uniformly random directions? If not, then let's talk a little bit about our next homework assignment. And to do that, I'm going to play for you basically the visualization that you're going to create at the end of the assignment. So just as a bit of a prelude before I play this, the way that, so how many of you are familiar with gradient descent? Can you just show of hands? So gradient descent is the most simplest optimization algorithm. So the way that it works is you're trying to optimize some function. You have some current points. And what you do is you look at the gradient of that function, which is going to point to you in the direction that increases the most. And if you want to decrease the function, then you head in the negative gradient direction. And you take some step size in that direction, and then you repeat that over and over, maybe changing the step size or doing some more complicated things. And eventually you get to smaller and smaller values of the function. And if it's convex, it has a unique optimum, and then you will find that optimum eventually, okay? So just as a broad outline, stochastic gradient descent works almost the same way, except for the fact that you don't know the gradient of the function, okay? So the gradient usually tells you in which direction the function is going to rise or fall. In stochastic gradient descent, instead of having the gradient, what you have is a random variable whose expectation is the gradient, okay? So that means that the gradient could be pointing left, but this random variable, when you call stochastic gradient descent, might accidentally point you to the right instead, okay? So you might sort of take several steps in the wrong direction. But I know that if I call for this same point, I call stochastic gradient many, many times, and then I take the average of all the results, then that's going to point me roughly in the direction of the gradient, okay? So what you're going to see here is an optimization that's actually doing stochastic gradient descent. And because these gradients are stochastic, the points are going to be bouncing around in all kinds of directions. So the optimum is going to be at one particular location, and typically gradient descent kind of takes a nice path down to the location that it's headed to. But here we're going to be bouncing all over the place, potentially quite often in the wrong direction, okay? So this is just a 1D example of optimizing a parabola. So this is the path, and that's the known optimum value here. So this is a slightly different function, and again, as you can see, stochastic gradient descent was sort of doing a bunch of walking in the wrong direction, but eventually it kind of gets down to the optimum. This is a different stochastic gradient, so different random variable that also has an expectation equal to the gradient. The next one is a 3D example. These are just 2D examples. So in 3D, you can see it's sort of bouncing all over the place, but sort of heading in the right direction. And eventually, we're going to implement this algorithm on a 700-dimensional example, like over 700 dimensions. And this is simultaneous runs from different initial conditions, okay? So for the next homework assignment, you're going to produce all of these visualizations. And then in the homework assignment after that, we're going to run stochastic gradient descent on a real-world example with about 800 dimensions and actually get some interesting results. So let's go over what the algorithm actually does and why it works. And if you're curious, that next homework assignment is already posted online here. So I just want to briefly go over this, what's posted, because essentially what I'm going to do is explain what's posted here, okay? But in a much greater detail than what's written in that PDF file. So at the beginning, you're going to define a bunch of parabolic functions. And to do this, you're going to do some interesting definitions of interfaces. And then over here is a very brief description of stochastic gradient descent. So what you want to do is minimize some convex function f of x over some constraints. And the way that I've written those constraints is just x and capital X. But those constraints could be linear constraints or some other complicated thing. There's a step size, and this is the way that the steps change with the iterations of the algorithm. So on the ith step, you take a S0 over I to the gamma step size in the direction of the stochastic gradient. And the steps are basically like this. You have your current point x minus 1. you have your step size, and this is a call to the stochastic gradient. So that's a random variable, right? So we're taking, this looks exactly like gradient descent. The current point minus the step size times the gradient. But here, instead of having a gradient, we have a stochastic gradient, a random variable that quite often might point us in the wrong direction, okay? And then this is just a projection step in case you're actually doing something constrained. And here are some sufficient conditions for the algorithm to work. You can change these. It still works under other conditions, but these are the ones we're going to use. First, the function actually has to have a minimum, okay? So if it doesn't have a minimum, for example, if it's a line and it's unconstrained, the algorithm's going to go on forever. You're never going to find a minimum, right? So we're assuming the function's convex and has a minimum. The second one is that the stochastic gradient is bounded. So that random variable, like I have to know some bound on its magnitude, okay? So, and if that's not true, it's very easy, and maybe I'll have you run some examples to show that the gradient descent algorithm might actually shoot off to infinity. Even though your function has a nice minimum, even though your step sizes are decreasing, things could sort of go haywire if this is not true, if the stochastic gradient is not bounded. The second one is we start not too far away from the optimal point. And again, there are some nice examples. We're going to see it maybe in the second homework assignment where if you start too far from x, like it might take a really long time. And then the fourth one is that the step sizes sum to infinity, but the sum of the squares of the step sizes is finite, okay? So I hope that now you can see why it might be useful to see a proof of this algorithm, okay? Because if you look at these assumptions, you might say, look, like that's really weird, right? Like look at this condition on step sizes. Like they sum to infinity, but like their squares are finite. What the heck is that? Like what the heck is this about the stochastic gradient getting bounded? That makes no sense. It's a perfectly fine function. Like it's convex, it's smooth. Like why can't I optimize it, right? So what we're going to do next is go through the proof of this algorithm to understand why it works and where these conditions actually get used, okay? Okay, so let's just begin here. So let's f of x is the convex function we want to minimize. And for simplicity, I'm going to drop the constraints. Okay, so what we want to solve is just minimize over x f of x. Right, so what's written in the homework assignment is that there's this other constraint, right? Like x has to be in some bounded set, like convex set cap x. But here, just to make the proof simpler, I'm just going to say that x is unrestricted. And I just want to minimize f of x over all x's, okay? Some other definition is that xk is going to be the kth iterate. Delta xk is going to be a stochastic, unbiased subgradient. Okay, so let's go over these three words. So what does it mean for this to be stochastic? It basically means that it's a random variable, right? So I stick in the same xk into it twice, I might get different answers out, okay? So it's a random variable, and in particular, it's a random vector, okay? So because it looks like a gradient. So it has the same dimension as the gradient of f of x, okay? And so just a quick question for you. If f of x is from Rn to R, what's the dimension of the gradient of f? How many pieces does the gradient of f have? Yeah, it has n coordinates, right, for each one of these inputs. So this means that this function has n inputs, and it's going to produce one output, and so the gradient's going to have n coordinates to it. So the first word means that it's stochastic. The second word, unbiased. So does anybody remember what unbiased means from statistics or any statistics class that you've taken? It's a property about the expectation. So it means that the expectation of xk it means that the expectation of this random variable is equal to the gradient of f, okay? And this is actually a bit like an even stronger condition than what we need. So usually people write this. Instead of saying equal to the gradient of f, what they'll do is they'll write that this expectation is an element of the subgradient set of f of xk. Okay? So in particular, what this means is that the only property I need of this expectation is the following, that if I look at f of z, then that's bigger than or equal to f of x plus the expectation of this subgradient at x times transpose times z minus x. Okay, so I just want to visually interpret this for you. So by the way, if this was a gradient, what would this be? Like if here, instead of writing expectation of subgradient transpose, I had written just gradient transpose, what would this expression be? Say again?
If it was a gradient?
Yeah, so if I had written gradient instead of expectation in this last line, what would just the right-hand side of this inequality be? Yeah, tangent line. Or another way to say it, a first-order Taylor approximation, right, around x. And that's exactly kind of what a subgradient does. Okay, so in terms of a picture, if this is my function f, and this is the point x, what a subgradient does is it gives you a line that underestimates the function. Okay, so for continuous functions, for functions that are continuous at x, it's exactly the tangent line. But it turns out subgradient descent works really well, just perfectly fine, on functions that are not continuous. Okay, so for example, here's a function. Like let's say that this is f of x. And let's say that we're at this point, right at that kink point. At that point, there's actually many subgradients, right? So all of these different lines, all of them have a slope that's a subgradient because all of them underestimate the function in this way. Okay? So for continuous functions, a subgradient is pretty much the same as a gradient. But when we have discontinuity, when we have sort of kinks or non-differentiable functions, then we might have many vectors that are in this subgradient set. But anyway, that's the property we want. We want that we get our underestimate of the function if we walk in the subgradient direction. Okay? Okay, so we'll let sk be the kth step size. And in particular, let's define it like this. It's going to be f0 over k to the gamma for gamma in 0, 1. Okay, so the left-hand side here is open and the right hand is closed. So gamma could be 1, but let's just say for now it's not 0, even though it actually turns out the algorithm works perfectly well, even if it's 0. Okay, so then the actual algorithm just works like this. is just xk is equal to xk minus 1 minus sk times the stochastic subgradient at xk minus 1. So the only difference between what I've written here and what's on the PDF of the homework assignment is that I took out the projection step because a projection from Rn to Rn, you're going to get the same point, okay, because we don't have any constraints here. Okay, so one other definition that I need is that Z star k, I'm going to call that the minimum of f at x1 up to f at xk. So in other words, the algorithm sort of walked through k points, and Z star k is going to be the smallest function value that I've seen so far through this entire sort of randomly walking algorithm, okay? Okay, so let's continue to our assumptions. And that's the main reason for doing this proof, is to understand why these assumptions are important for the algorithm to work properly. So what were they? So the first one is that f has a minimum. So let's say that's x star, and the function value there is z star. Another one of them was that the expectation of the subgradient's norm is bounded above by g. And another one was that we don't start too far away from the optimal point. And then the last one was this weird one about the step sizes, that if I sum from 1 to infinity of Si, I get infinity. But if I sum from 1 to infinity of Si squared, what I'm going to get is less than infinity. So I'm going to get something finite. Okay, so can anybody tell me just a sequence from like Calc 1 class? Like you may have learned this in Calc 1 or Calc 2. A sequence where the sequence sums to infinity, but the square of the sums, or the sum of the squares, is finite.
1 by k.
Yeah, 1 by k, right? Because this ends up being like log n, and this is 1 over the squares, 1 over k squared, which is finite, right? And in general, that's where you can see these step sizes. So what do these step sizes look like? They're S naught over k to the gamma, and gamma somewhere between 0 and 1, right? And generally, that's going to give us this property that the step sizes are not summable, but the step sizes squared are summable, okay? So that's why these step sizes have this weird format. Okay, so let's now do the proof to see where these assumptions actually come in. So I'm going to start by writing an expectation here, a conditional expectation. So I want to look at how the distance between k plus 1 and x star, I want to look at the expectation of this distance given that I'm currently at xk. Okay? So that kind of makes sense. I want to just see, as I'm stepping through this, what's going to happen to these distances. And hopefully, we're going to see that somehow these distances are going to get smaller, right? But right here, I'm not looking at the expectation of this. I'm looking at the conditional expectation of this. In particular, the kth location of the algorithm is itself random, right? The only thing that's not random is where I started. I started at x0, wherever that is. but like after k steps, I'm at some point that's like way down the line, and who knows where that is. So there's some distribution of the xk's. And so that's why we're looking at this conditional expectation. Okay, so to get an expression for this, the very first thing we're going to do is just substitute the definition of the algorithm, right? So the definition of the algorithm gives me an expression for xk plus 1 in terms of xk. So let's just substitute that in here. So that's equal to the expectation, and then here I have a norm, xk minus sk plus 1 times this stochastic subgradient at xk minus x star, and then the norm of this whole thing, and I'm looking at the expectation of that given xk. Okay, so I hope that makes sense to everybody. It's just a straight substitution right there, okay? So the next thing I want to do is, like this norm, I've written it right here, but it's really like a dot product. It's really just a dot product because it's the norm squared, right? And so that dot product, I want to just distribute things, okay? And in particular, one way you can think of this is like this. So think of this as perhaps xk minus x star minus sk subgradient or stochastic subgradient at xk. This thing sort of dotted with itself. So that's what that squared is going to mean for now. So this is a vector, and I just want to dot it with itself. And dot product distributes. So the first term I'm going to get is this thing dotted with this thing, right? If I square everything. Now, this first term, the xk minus x, is it random given xk? No, right? So given xk, that's a constant, right? And so I'm going to have the expectation of that constant, so I could just pull out the constant, right? So what I'm going to write here is just the norm of xk minus x star squared, right? So that's just that first constant. Okay, so now let's think of the second term. So the second term is going to be 2 times these things dotted together, right? So what is constant here given xk? Is this constant given xk? Absolutely. Is sk plus 1 constant given xk? Yeah, the step sizes are constant. They don't depend on where I am in the space, right? Is this constant given xk? Absolutely not. That's the stochastic subgradient, right? Okay, so let's write that out. So I'm going to have minus 2 times sk plus 1 times xk minus x star transpose, and then times the expectation of the stochastic subgradient at xk given xk. Okay, so that was the second term. And what about the last term? Okay, so the last term is going to be just this guy sort of squared, right? So what's constant there given xk? Sk plus 1 squared is constant, right? And this guy is still, that one is still a random variable. So here I have plus sk plus 1 squared times the expectation, but now I have the subgradient squared given xk. Right? So I hope you guys are all okay with that last sum n, right? Okay, so The next thing I'm going to do is take a look at just this middle term. Okay, so that middle term, what am I doing? I have x star. I've moved some distance away from x star. Maybe another way to think about it is I have xk, and I move some distance away from xk, and I'm multiplying it by the expectation of the stochastic subgradient. So what should I be able to apply here to get like a nice substitution? How about this? How about the definition of stochastic subgradient? So in particular, I'm going to write it, and then you can tell me why it's true, okay? So I'm going to say this is less than or equal to norm xk minus x star and then over here I'm going to have minus 2 sk plus 1, so same constant out there. But instead of this dot product, what I'm going to write is f of xk minus z star. And then I'm going to copy that last term, sk plus 1 squared, an expectation norm given xk. Okay, so let's see why I was able to do this. So any ideas? Given this? So z star was defined as f of x star. So that's my optimal location. Okay, so let's maybe plug it in here, right? So imagine that I am going to just apply that around xk, right? So what do I get? This is true for all these, or I guess we're getting confused here. But whatever I plug into the function here or here, this inequality holds true. So let's, in particular, plug in x star. So here I have f of x star is bigger than or equal to f of xk plus the expectation of the gradient at xk transpose times x star minus xk. Okay, so by just moving things around, so I can get basically the inequality that we have here, right? So you move things to the right side of the unequal sign, so you move both of the f's on one side, you have the expectation times x star minus xk on the other side, and you get that expression there. Okay, so that, I hope this makes sense. So this is our, we're applying the unbiased stochastic subgradient definition right here. Okay. Okay, great. So what we're going to do, so this is the stochastic subgradient. So what we're going to do next is take the expectation of both sides. Okay, so in particular, if you look at the left side of this inequality, there's something random there. Like, what's the random piece? It's xk, right? Similarly, on the right-hand side, xk is random, right? And so I'm going to take the expectation of both sides in terms of the distribution of xk. So on the left side, when I do this, I just get the expectation of xk plus 1 minus x star, but now not conditioned on anything, right? So this is the Tower property of expectations. If I take expectation conditioned on something, and then I take the expectation of that with respect to the distribution of what I'm conditioning on, I just get back the whole thing, right? So that's what happened to the left-hand side. So let's write down what happens to the right-hand side. So here I have the expectation of xk minus x star squared. So that's the expectation of this first term. On the second term, the only thing that's random is this. So I get minus 2sk plus 1 times the expectation of f of xk minus z star. And in the third term, what I'm going to do with the third term is the following. So this norm of the delta squared, do I have a bound on that? That was one of our assumptions, right? So that was less than like g squared, right? So I'm just going to say that this inequality, I'm going to apply my bound here. So I can just say it's an expectation, but I know all those numbers are less than g squared, so I can upper bound it by g squared. Okay? So what I'm going to write here is plus sk plus 1 squared times g squared. Okay? So we're getting somewhere really nice. So in particular, what did we do here? On the left-hand side, we have an expression of how far the k plus first step is from the optimal. And on the right-hand side, we have an expression on how far the kth step is from the optimal. And then there's some terms here. But the point is, I can take this inequality, and I can repeatedly substitute it into itself, right? So I could take this and replace it with a slightly bigger expression that involves xk minus 1. And then a slightly bigger expression that involves xk minus 2. And a slightly bigger expression that involves xk minus 3, and so forth, until I roll it back all the way down to x0, okay? So let me just do that. So if you do that sort of roll out this inequality recursively, what you get is that the expectation of xk plus 1 minus x star is less than or equal to the expectation of x naught minus x star. So that's the very last term that we end up with after we roll out everything recursively. We're going to get a bunch of these minus terms that are going to pop out. So every time that I do this rollout, I'm going to get one of these guys that pops out, right? So that's going to get represented by the sum. So minus 2 times the sum from I equals 1 to k plus 1 of si times the expectation of f of x I minus 1 minus z star. So that's me rolling out that second term. And then in the third term, we get something that looks like plus the sum from I equals 1 to k plus 1 of si squared times g squared. Okay, so because every time I roll out, I'm going to get one of these terms that pops out as well. Okay? Okay, so let's rewrite this a little bit. Or
Remove the minus.
which minus?
I don't know.
No. So what I was going to say is, this thing here is the expectation of a norm, right? And so that's definitely bigger than or equal to 0 because norms are positive, right? Okay, so now let's just take a look at this inequality. 0 is bigger than or equal to all those things on the right-hand side, and then I'm just going to rewrite that inequality by moving this second summand over on the left. So I have 2 times the sum from I equals 1 to k plus 1, Si times the expectation of f of xi minus 1 minus z star is less than or equal to the expectation of x0 to x star squared, that distance, plus the sum of the si's, I equal 1 to k plus 1 squared times g squared. Okay? So I think that's a relatively easy manipulation step. And then the last thing that I want to do is take a look at these things. So this is the expected value of what I'm getting on the I minus first sort of iterate, okay? And I have a bunch of these terms where I changes. So I'm going to make this left-hand side even smaller by substituting it with the smallest of these expectations, okay? Right? So that makes sense. If I substitute with the smallest of these expectations, I get something even smaller. So that's how I'm going to get this next step. So the minimum from I equals 1 to k plus 1 of the expectation of xi minus 1 minus z star is less than or equal to r squared. So the way that I got this r squared is this distance between x0 and s star. One of our assumptions was that it was not too far away. So that's where I got the r squared. Then we have this summand that's from I equals 1 to k plus 1 of si squared g squared. And then on the bottom, we have 2 times the sum from I equals 1 to k plus 1 of si. Okay? So now can you see why like the step sizes are really important? And why we have to have them be square summable finite, but when you don't square them, they sum up to infinity. In particular, imagine taking this limit as k goes to infinity, okay? What do we get on the left-hand side? On the left-hand side, we get something that's kind of like we want, which is sort of the difference between the best function or the expected value of the best function value that we've seen so far. But what do we get on the right-hand side? Like, it's clear that we want this on the left to basically go to 0, right, if my algorithm's working correctly. But the only way that that's going to go to 0 is if this thing on the top is finite and this thing on the bottom is not, right? And so that's why I want the step sizes to sum up to infinity, but I want the top to be finite, which included bounding the gradient, it included bounding the distance from x star at the beginning, and it included that the sum of the squares of the step sizes has to be finite, okay? And there's a couple of other steps you can do here. So you can apply Jensen's inequality. So this thing immediately implies that this minimum goes to z star. And then if you apply Jensen's inequality, then we had a definition of zk star So if I scroll back up here, our definition of zk star was different. So our definition of zk star is the minimum of the f, right? So zk star is itself random, right? So basically, like, we're switching minimum and expectation. So that's what Jensen's inequality allows us to do. Here, the minimum is after the expectation, whereas beforehand it was before. So here, the minimum is before the expectation, and here the minimum is after the expectation. So the expectation of zk star goes to z star. And you can show various other things. Like, using a more complicated algorithm than what I showed you in class, you can actually show that the sequence of x's also converges to the x star that you want, okay? But the main reason I wanted to show you this was really this step right here, which shows you why all of those assumptions that we list for the algorithm are sort of critical to making it work right. And so much so that if they're not true in your code will not work, okay? Like, the algorithm's going to give you crap answers. Okay, so let's just spend a couple of moments talking about how to get stochastic subgradients on parabolas, okay? So let's say that I have f of xy is equal to alpha 1 x squared plus alpha 2 y squared, okay? So these are the kinds of parabolas we're going to work on your homework assignment. So they're slightly less general than the most general parabolas, but they're going to look like this. So we're going to have some coefficients times x squared and some coefficients times y squared. So who can tell me what the gradient of f of xy is? 2 alpha 1x, 2 alpha 2y, okay? So that's the gradient. So now I want a random variable whose expectation is going to be equal to this gradient, right? So that's what's going to allow me to do stochastic gradient descent. So here are, these are the two things that you're going to implement. So the first thing that you're going to implement is pick a random coordinate and return the gradient of that one only. Okay? So this one half the time, it's going to return something that looks like 2 alpha 1x. And a half the time, it's going to return something that looks like 2 alpha 2y. Does that make sense? So it picks a random coordinate and returns sort of the gradient just for that one coordinate. But does this random variable, is its expectation equal to the gradient? Or this random vector, is its expectation equal to the gradient? Yeah, I need to double it, right? So I'm going to multiply this by 2. Okay? So, but this one, it's really easy to show that that its expectation is equal to the gradient, because you could just do it coordinate-wise, okay? So the second one I'm going to have you implement is you're going to pick a random direction and project the gradient in that direction. Okay? So what I mean here, if you, in particular, is that the stochastic subgradient, so this is going to be our first stochastic subgradient at xy, and it's easy to see that that one has the right expectation. So this one at xy is going to look like this. So U transpose dot grad fxy dot U, where U is just uniformly random direction. Okay? And that's why we talked about generating uniformly random directions a little bit earlier in class. In this one, it's not quite as easy to see that its expectation is equal to the gradient, okay? So what I have, what's U? It's a bunch of normals that we've like normalized that gives me a uniformly random direction. But before I know that the algorithm's going to work, I want to sort of make sure that the expectation of this thing actually is going to give me the gradient, okay? And maybe this is where we're going to pick up last time or next time, but before we quit for today, I just want to give you another one. So here's another one that works, should work just as well. So xy is equal to grad f xy plus, let's say, nu, where nu is just a normal with mean 0, 0, and variance, let's say, 1,000, 0, 0, 1,000. Okay, so why is this one a stochastic subgradient? What's its expectation? Just expectation's linear, so this is a constant. When I take the expectation, this is going to be a constant, and what's the expectation of the second guy? 0, right? So this one kind of like most of the time sort of points in the direction of the gradient, but we've added like a whole bunch of noise that's like a uniformly random other direction, right? That comes from this Gaussian that's going to be bouncing us in all sorts of directions, okay? But what we're going to, I'm only going to have you implement 1 and 2, but once you've implemented 1 and 2, it's going to turn out that, and you'll see based on the assignment, that implementing other ones is going to be relatively easy for you by the way that we've structured the code, okay? But at the beginning of class next time, we're going to prove that 2 actually is a stochastic subgradient, so algorithms should work for it when we use it. Okay, thanks a lot for listening, and I'll see you all next time.